KI system call exit branch. So this sounds like functions which deal with, well, synchronization or some low-level stuff. And in fact, the reason for this is that Windows kernel adjusts to specific hardware which is run on and changes some body of the function to have better for speed, yeah, to be more effective. I was speaking with someone from Microsoft about this problem. Why is it done like this, and why isn't it possible to make a separate code section, let's say, well, alt text, for example, and put all the functions into the separate alt section, so it would be very easy to know that those modifications are just kernel modification, and these are not infection alarms. And the answer for this is, of course, the speed, because as he said, the kernel is optimized. The kernel code is optimized in such a way that it fits into specific caches. So the position of each function should be, well, like it is, and it would make an impact on effectivity if we move it to the other section. So, no matter if it's really true or not, we need to deal with this kernel modifications, because in other case we will make lots of false positives. No matter if it's really true or not, we need to deal with this kernel modifications, because in other case we will make lots of false positives. These are the modifications in HAL module, HAL DLL, hardware abstraction layer. We see a little bit more modifications. But the observation here, which is very useful, is that all modifications replaces nulls with some bodies. So we can expect that these were the places left to be filled upon, well, execution. So it's easy to filter it out. Can you switch to the slides? So if you want to avoid HAL modifications, we can just make use of these observations. That if it's O to XX, then it's a kernel self modification, and it would be very difficult to write a rootkit, in my opinion, which would work by just modifying those files. Actually, it would be very difficult to write a rootkit which would work by modifying HAL code section, and this is the reason why I don't check HAL section integrity in SVV. Although you can use the switch A to check all modules, but in default mode it's not checked. NTOS kernel is more problematic because it's a very important module from the rootkit point of view or backdoor point of view, and there are lots of stuff which can be altered by rootkit to I tested on many systems, are just not to something. So these are 1 byte modifications. So this is pretty obvious because somebody put a knob just to mark that this may be modified in the future. And the rest are just modifications which are more than 1 byte long, are just the number of them is very little. And of course it's very difficult to write a rootkit which would, if not impossible, I think it's impossible, which would work by just 1 byte modifications, right? Okay, this was the demo which I showed you. Any questions up to this point? Is it clear or, yeah? Okay, now about innocent hooking. Not making alarms where there's antivirus monitor or something like this. So first we need to, I would like to define several types of hooking which you can observe in the system. But before this, just a small definition. What is missing and hidden files? What I mean by missing and hidden files. So file is missing when create files and this file returns error files. So the file is not present basically. And file is hidden when file first file or file next file on one of the on this file on one of the directory which contains this file fails. But in most cases, all hidden files are not missing. Is it clear? For example, if we install Hacker Defender rootkit in a folder rooted, right? And so Hacker Defender will make it invisible, this folder, right? So if we list the C/ directory, we didn't see we will not see rooted folder. So find first file will not return this directory, right? But if we know the name of the magic directory, and if we try to execute create file on this path, it will succeed, right? So this is important to distinguish hidden and missing files. Any question? Anybody confused by this? Okay, typical innocent hooking is like this. This is the function which we hook. For example, this function might be kernel debug print function, and it will be hooked by debugv.sys module by sysinternals. If we use debugv by sysinternals, and it will just hook to some other function which will be in debug.sys module or whatever. Or if we consider antivirus monitor, this could be, for example, I don't know, read file, right? Read file or create file, and it will transfer execution to the root antivirus provided function. And the observation is this function will be located in a valid module, and this module will be will has corresponding image file which will not be missing nor hidden. Well, it's really obvious that the rootkit cannot use this type of hooking because rootkit is interested in hiding its file, so it will not be visible. Malicious hooking, this is what I just said. So this could be like this. We transfer the execution to some module, but the module file is hidden, but it may be present. Debugger-like hooking. This is actually used by most of the tools like the system monitors from sysinternals. They are just one executable, well, like registry monitor, right? Regmon. Regmon consists of one module, one executable module, but when we run it, it extracts from its resource section. It extracts driver, rec something. And put it in Windows System32 drivers directory, loads it, and then deletes the file. So we have a situation when the hooker's code is in the valid module, and the corresponding image file is not hidden, but doesn't exist. Another malicious hooking. This is mostly used by more advanced rootkits. Again, we have a hooked function. Well, let's say it's registry rec key registry key enumeration. It's hooked to the rootkit code, and the rootkit code does not belong to any module in memory. So if we traverse the list of loaded modules, we don't find the modules which has start and end address, which could contain this code. So again, this is an obvious sign of the malicious hooking. And to be complete, yet another possibility is that rootkit does not use simple hooking, because all those things, as you probably just noticed, requires that SVV or any other code integrity checker will resolve this code as a proper assembly, will disassemble properly. So the SVV can know the target address. If this is jump something, we need to decode the jump opcode, we need to add the address to the relative address and find the target address, right? But the rootkit can use some obfuscated code, like some polymorphic code, to make this jump, or can put the jump somewhere here, or, well, can make it obfuscated. So the code integrity verifier will not be able to decode the target address, right? And for example, recently I saw on rootkit.com an article how to bypass Vice. Vice is another integrity-based detector written by Jamie Butler, and it doesn't work like SVV. It doesn't compare code sections. It just searches for jumps at the function prologues, and if it finds a jump, it will report it as an infection. But so this author, which I don't remember, developed technique to make it obfuscated, so Vice will not check it, will not find it. But in our case, this is not a problem for us, because if we detect code which we don't know how to resolve, which don't know how to decode, we just say, okay, this is malicious hooking, because I'm not aware of any antivirus monitor, neither any other implicit tool which would be interested in putting obfuscated code into the functions. It was this one. I'm sorry, this is the one which I was talking about. And yet another thing which we should take care of is service descriptor table, well, service table modifications. Service table, in many cases, is pointed by KI service table address, and this symbol is located, well, the address pointed by this symbol is located inside text section of entire kernel exec course. So if we detect modification in KI service table, then we need to treat it in other way. We are not trying to resolve it as a jumping code, but just as an absolute address, right? The problem here is that not always, well, because the obvious way, of course, KI service table is not exported, right? Because this KI is a kernel internal symbol. So the obvious way from finding a service table is this expression, right? This is KE service descriptor table, which is exported, of course, which binds to the service descriptor table, and first element and first field of this element is just a pointer to this. Well, it's just a pointer to the service table which is currently used by the system. I hope everybody knows this. Well, this is obvious, right? Or not? If anybody have some experience with SDT rootkits? No? Okay, so well, basically, KI service table could be, in most cases, found by this expression. But not always, as it turned out, because well, some antivirus monitors, like Kaspersky antivirus, use their own service table, so they modify it to point to their own service table, so we don't know where KI service table is. And a guy called 210, well, several months ago, published article on rootkit.com about how to find it in a very smart way. So this is the way SVV is uses here. Okay, finally, before the SVV demo. Oh, this, I think the red cable is not connected well. Because this is red and this is more red. Like, well, it's just more red. If it was connected good, you would see this. So this the SVV on the output gives one of the 6 verdicts.